All right, babies, welcome back. So in this quick little video lesson, we're going to just go through, again with Coulomb's law, how to find the electrostatic force, and then how to relate this to Newton's laws on balanced and unbalanced forces that we've talked about in the past. So we're going to go through two examples here, just one example on balanced forces and the next one on unbalanced forces. So just remember, balanced forces are when all the forces acting on an object are going to cancel each other out. They're going to be equal and opposite, which means that that object is either going to be at rest or be moving at a constant speed. In unbalanced forces that we'll look at here in just a second is when the forces of an object are obviously not equal and opposite, so there's going to be what's called a net force, or a part of that force that's going to be unbalanced, and that's going to cause an object to accelerate. So here we have a negatively charged rod with negative 85 nanocoulombs of charge. Is being used to balance the downward force of gravity on a 0.02 kilogram balloon that also has a charge of negative 63 nanocoulombs. And I want to know how far below the balloon must the rod be held in order to balance the balloon. So think about here, we have a balloon that's in the air, and below it we have a plastic rod charged negatively, okay? They are both charged negatively, so the rod is negative and the balloon is negative, but the balloon wants to fall. So think about the forces acting on the balloon. We would have the force of gravity pulling down on this object because it is a real-life object. There's gravity acting on it. But because they're both negatively charged, there's going to be an electrostatic force that is opposing gravity, that's pushing against each other, because two negatively charged objects would repel. So when I look at the force of gravity and the force of electrostatic force, and if it says here it's going to be held in balance, that means that these two forces must be equal and opposite in terms of their magnitude and direction. So I want to know how far, what is the distance between these two objects will that balloon need to be held in order to keep it balanced? That's our question here. Okay, so obviously if we think about the two forces, the force of gravity is something we should know how to calculate, which is the mass times that value of gravity, which is 10. This is something that we should be able to find right away. If I know the balloon is 0.002 kilograms, then if I multiply that by 10, I know that it has 0.02 newtons of weight, or the force of gravity, which is pulling it down. Since these forces are balanced, here's what I know, that the force of gravity and the electrostatic force are both going to equal each other if it's in balance, which means that the electrostatic force is also going to equal that 0.02 newtons. And this again is what it means for things to be balanced, is that the forces are equal and opposite. So if gravity is at 0.02 newtons, then the electrostatic force is the same. So using Coulomb's law then, if I know the electrostatic force is 0.02, well, I know using Coulomb's law that the electrostatic force can be found using this equation, K, Q1, Q2 over the distance squared. So I can set that equal to that K value, which is 9 times 10 to the 9th. I know the charge on each balloon, on the balloon is negative 85 nanocoulombs, so that's negative 85 times 10 to the negative 9th. I know the charge on the balloon is negative 63 nanocoulombs, so times 10 to the negative 9th. And my goal is to figure out the distance between them. Okay, now the key thing here when we're trying to find the distance, that notice in our equation, distance, God bless it, distance is squared. So our goal is to figure that out. So we just have to do some algebra here. First thing I'm going to need to do is to multiply all three of these things together to figure out what that is going to give me. So simplifying that on top, I would get 0.00048. Okay, again, that's going to equal that force. My goal is to solve for the distance. So algebraically, what I'm going to have to do is, there's a quick way to kind of do this, is I'm going to have to take, in order to solve for distance, I got to get it out of the denominator. So that means I'm going to have to take that whole distance square part and really multiply it across. So what I'm going to do just quick is I'm just going to swap those two things out. I'm going to switch the force and that distance. By doing that, I'll get the distance squared equals that value of 0.000048 divided by that force of 0.02 newtons. And then the last thing I would have to do in order to solve this is to, whatever I get from that value, is to get rid of that square as a square root. So algebraically, this is a little bit more complicated. Okay, when you square root that and solve it, you should get a distance of 0.049, so 0.05 meters. So that's about 5 centimeters apart. Okay, so think about in in the class, we're going to do this levitating lab where you're levitating a tinsel. It should be something that is below a meter, so 5 centimeters would make sense. So again, we use the idea of things being balanced. We just related gravity and that electrostatic force, looking at their values, figured out that if they're balanced, they're equal, and then using Coulomb's law. And obviously with Coulomb's law, the algebra is just a little bit more difficult. Okay, so now we're going to look at the case when things are unbalanced. We're going to do the similar situation with our balloon and our rod. So let's say that I have a balloon and now I have the rod. The only thing that's different, and you'll notice that our answer from the previous example, we got 0.05 or 5 centimeters. Here we're looking at a distance of 0.12. So now it's going to be held a little bit further apart. So think about the distance between them as that 12 centimeters or 0.12 meters. We still know that the rod is negatively charged, that the balloon is negatively charged. So again, forces-wise, you're going to have the force of gravity. Okay, now just because it's held at a different height, that does not change that the force of gravity should be the same value. Should still be, well, in this case, I guess we have a different number. So it's still going to be that mass of 0.001 kilograms times 10, which would give me 0.01 kilograms. Okay, so we can still find the force of gravity. Now, the only difference now is we're going to have to find that electrostatic force between the two objects. And again, I'm given all the variables. I'm given the two charges of negative 75, negative 83, and a distance between them. So I can find that electrostatic force using the Coulomb's law equation. So it would be 9 times 10 to the ninth, which is again that constant value, times the two charges, so 75 nanocoulombs, so times 10 to the negative ninth. We have 83 nanocoulombs, which also be 10 to the negative ninth. Okay, I know they're both negative, so it's going to be a force of repulsion. And then here I'm actually given the distance of 0.12 meters. So because I'm given all the values, I can actually figure out what this force is. So using my calculator, I'll figure out that the electrostatic force between them is going to be 0.004. I'll just round that, newtons. Okay, so here if I know that the force of gravity is 0.01 newtons, and just recognized here that I wrote down the wrong units, that should be newtons. And then now I know that the electrostatic force upward, I'm going to draw that arrow to scale, is much smaller at 0.004 newtons. I now know that those forces are unbalanced. Okay? Since they're unbalanced, if I were to subtract these 0.01 newtons minus 0.004 newtons, that's going to give me the net force, which should be about 0.006 newtons. So that, again, is the net force, and that is going to be what the balloon is going to experience. Now, because gravity is the larger of the two, that means that at this distance, that balloon is going to fall. And we can go a step further, and use Newton's second law that, hey, there was a relationship that if something experiences a net force, then it's going to accelerate. Knowing the net force and the mass, which we do, we could figure out the rate at which that balloon would accelerate. So kind of putting this all together, if I know then the net force is 0.006 newtons, if I know the mass of the balloon is 0.001 kilograms, I can find its rate of acceleration, which would be about 6 meters per second each second. And because, again, gravity is the larger of the two forces, I'll show this on my diagram, that means the balloon would accelerate downward at a rate of 6 meters per second each second. Okay? Now, again, what would happen here is it's going to fall downward until it gets to a point where the forces are going to balance out. And this is how we're able to make things levitate, is that as this balloon falls, this electrostatic force, because it's dependent upon the distance, this electrostatic force will get bigger by the inverse square law. So what we'll eventually see is that that force will get bigger, the acceleration will get smaller, and therefore, eventually those two forces will balance each other out, causing the balloon to levitate. Okay, so it's kind of complicated here, but we can go back and apply this idea of Coulomb's law to Newton's laws of things being balanced and unbalanced.